next speaker is Alessio Fontanarossa, who's going to talk about nuts, bolts, and spindles. Please.
Okay, thanks. So let me start by thanking the organizers for the opportunity of being here and giving this talk, which is about this hopefully upcoming paper with these gentlemen, Kevin Crisafio and Dario Martelli, which are here in the audience. So I'll start with some introduction about nuts and bolts, then I'll move to the construction of spindle bolts and their orographic free energy, which is the main topic of this talk, and then I conclude with some comments. Okay, so the expression nuts and bolts comes from Gibbons and Hawking, where the interest was on gravitational instantons, which are self-dual solution to Einstein theory, and so they are necessarily Ricci flat. And in particular, the name Nut solution comes after the famous Taub Nut solution generalized later by Hawking, which has the topology of R4, or quotient of it. And instead, the Taub-Bolt solution name comes after the famous, again, Iguchi-Hanson solution, generalized later on by Hawking and Gibbons, which has the topology of C over S2, fibered in a non-trivial way over S2. And in this case, the metric is asymptotically flat, and the boundary was just around the trisphere mod Z2. Then there is a vast literature about this topic, which obviously I skip, and then I arrive to some notion of nut and bolts, which is useful for practical purposes, and it's valid also for anti-de Sitter spacetimes. So for me, from now on, a nut solution will be just a regular solution on R4, or quotient of it, with a nut, which is a zero-dimensional fixed point set under some Killing vector. And similarly, a bolt solution will be a regular solution on OP with a bolt, which is a two-dimensional fixed submanifold under this vector. So I can now show you this important nuts and bolts solution in ADS. So this is important for holography, and has been found by this collaboration of Dario, Passias, and Sparks, and generalized later by Toldo and Villet. And in this case, the metric is asymptotically locally ADS4, with the boundary, which is a squash trisphere, with this S being just the squashing parameter. And in particular, it is invariant under SU2 times U1, from which the name biaxially squash trisphere. Moreover, the solution is further subdivided into cases according to the values and the relation between these four parameters in the solution. And so we can have an half BPS class, a quarter BPS class, and also a self-duality condition, which generalizes the Iguchi-Hanson and Taub-Nut solution I told you before. So this solution will play a role later on, so by now keep it in mind. Okay, another class of solution, of important solution is this one, which is again asymptotically locally ADS4, and is a quarter BPS solution. And in this case, the metric is written in this standard let's say, Carter-Przebanski form with a non-trivial gauge field and two quartic functions. In these formulas, Q is a radial coordinate, which goes from Q plus and infinity. And this Q plus is just the largest real root of the function Q, whilst the other coordinates, P, tau, and sigma, are just some angles. And in particular, P ranges between P minus and P plus, which are, again, the largest real roots of the function P. Here we have 6 parameters related once again by supersymmetry, and these are the two BBS constraints that you have in this type of solution. So, provided this condition hold, which is a constraint on the periodicity of one of these angles, the boundary has the topology of a squash trisphere. But the fact is that in this solution, only the case in which Q plus was equal to P plus has been considered, and so the regularity analysis near this blue point imposes that N is equal to M and P equal to Q, and in turn this implies that the solution is self-dual. Moreover, this blue point is a nut, so this is a nut type solution. And once you have imposed these conditions, you are left with, again, a squash trisphere with two free parameters, but now the symmetry is U1 times U1, so this is a different squash trisphere than the previous one. So the idea is now to find in this class of solution, not a nut, but a bolt, and in particular, a spindly bolt. Okay, so as I said, the goal now is to construct a U1 squared invariant solution on this total space, which now is the fibration of C over the spindle. And as you know, also from the previous talk, the spindle is just a true sphere with conical singularities at the poles, characterized by these coprime integer m minus and m plus. And so we have this standard picture of the spindle as obtained by the quotient of S3 with the weighted action of U1. And in particular, the presence of this spindle in the gravity side is also important for the holography with orbifolds, as discussed by Dario Martelli in his talk. So the idea to reach this goal is, first of all, to separate the point Q plus and P plus, because in this case, we can hope at least that there is a Killing vector, which degenerates at Q plus, and we can use the P angle and another angle to describe just the spindle. So the upshot of this analysis is that the metric cannot be regular anymore for n equal to m and p equal to q, and so our solution won't be anymore set-dual, but still it will be a quarter BPS solution. So first of all, change variables from this tau and sigma to this more convenient theta 1 and theta 2 on two patches on the spindle, such that the boundary metric takes this form. And we can now start imposing some constraint on this metric. So we impose these spindle conditions, for which the first line in this formula has indeed the topology of a spindle. Then we require also that the fibration is well defined in an orbifold sense, which translates in the fact that this integer here should be an integer. And once these conditions are imposed, we are left with a boundary which is a squashed length space. Moreover, we have to impose regularity near the bolt, which I recall is located at Q plus. And if we are able to impose all these four constraints at the same time, we have achieved exactly our goal, which is to obtain a spindly bolt. Moreover, we are left again with two free parameters, because we started with these 6 parameters in the solution, plus the periodicities of these two angles, minus 2 constraints from BPS, and 4 constraints from this regularity analysis. Okay, one last interesting point here is about the quantization of the gauge field, because obviously we have to integrate the field strength through the spindle itself, and this is the result. This sigma is exactly as in the previous talk. And the key point here is that we can have in the same class of solution both the twist and the anti-twist. So by this I mean that there are values of the parameter in the solution for which sigma is equals to 1, and so we have the twist, and other values of the parameter for which sigma is equal to -1, and indeed that we have the anti-twist. Okay. So as I said, we have these two families divided according to the value of this sigma, and we want to compute their holographic free energy. So we can start the standard procedure with renormalization, okay, and we obtain this result, which is valid for both the family. But now I want to point out that these parameters appearing here are different in these two families. So we have to specify their values to go on. And the result is that for the twist case, the oscillation is simple and basically is constant and depend only on the integers of the solution. Whilst in the anti-twist case, the situation is much more complicated, and this expression is the best one we found, but it's quite involved. Indeed, we have to take this Q and put here in various places. But there is one important point now, which is the fact that, recall that we have 2 free parameters, but none of these appear in the on-shell action for the twist case. Whilst, even if it's not evident from this expression, only one of these appear in the anti-twist case, which is this tilde Q plus in red here. Okay, this is our result, which is quite complicated. And from this point, we can start taking some limits. Indeed, first of all, we can collapse P plus and Q plus, and we obtain again the set dual U1 squared NAT solution with their holographic free energy in this type 1 family, a type 2 family, as introduced in this paper. And these correspond to the twist case, and this to the anti-twist case, and you see that indeed this on-shell action is constant as for the twist case. But this is not constant. There is one parameter, which is this ratio, as in the anti-twist case. Then we can do another thing. We can collapse P plus over pi minus, but this should be a scaling limit because we have to do this operation by keeping the sides of the bolt fixed. And in this operation, the symmetry U1 squared is enhanced to SU2 times U1. And so we obtain exactly the SU2 times U1 spherical bolts of this reference. And we obtain exactly the holographic free energy both for the quarter BPS solution and the half BPS solution. And again, this is constant, while this there is a parameter, which is the squashing I told you before. Finally, we can collapse everything to a point, which is in this case. And now we obtain exactly the SU2 times U1 invariant nuts with, again, both the quarter BPS and the half BPS solution. Of relaxation, sorry. Good. So just to conclude, we have found a complicated space of solution which all comes from our spindly bolt with U1 squared symmetry. So in this picture, in this side, everything comes from this quarter BPS solution with twist. And in the other side, everything comes from the quarter BPS solution with anti-twist. Okay. Another comment is that we can add some parameters to our solution. In particular, we can add acceleration. And so we move from a Cartan-Plebanski solution to a Plebanski-Demianski solution. But still, we are able to impose the topology of OT with some spindle. And this should have some relation with the accelerating black holes with spindle in the horizon, as discussed in this reference and in the Darius talk. Okay, then there is everything from the other side of ADS-CFT, and many things have been done in these years, but there are still some missing points. Indeed, nothing has been done for these half BPS spherical bolts with SU2 times U1 symmetry, and obviously everything has still to be done for this quarter BPS spindly bolt solution that we have found. And this must be a generalization of what Dario said in his talk and what Edoardo will say in next talk, and he's written something in a companion paper by Martelli, Inglese, e Pittelli. Last comment is about extremization. Okay, I don't have the time to enter in the details of this slide, but the point is that we can follow some equivalent localization approach as introduced in this reference here and as explained by Alice in her talk 2 days ago. And okay, the upshot is that following this procedure, we obtain exactly our results for both the twist and the anti-twist case. But we can do something different. Indeed, we can take this formula as it is, and we notice, it's not evident from this slide, but we notice that it depends only on one parameter, which is this Z, which is basically the ratio of the entries of this bilinear constructed upon the Killing spinner. And we can try to extremize this function with respect to the variable Z. And the result is that at the extremal value, this procedure gives exactly our wrong shell action in the twist case, but for the anti-twist case, the result is basically wrong. So I don't have too much to say about this because it's an open problem and we have to work on it. But just a little comment is that this can be related to the fact that, as explained in this 10-year-old paper, regular nuts are characterized or by Z equals to -1, where this is the same Z, or Z greater than 0. And this is exactly the behavior we have found because we have two classes, we have the twist and anti-twist, and in the twist case, everything is just fixed, like here. In the anti-twist case, instead, we have a free continuous parameter, which is positive also in our case, and should correspond, at least morally, let's say, to this condition here. So with this open problem, I think I can conclude, and so thanks for the attention.
Thank you. Question?
So I just want to make sure I understand. This is a new black hole solution that you found?
Okay, we are working in Euclidean 4 dimensions. So,
because I thought the solution was already known, but maybe I'm
I don't think
biased,
so,
you know?
but no.
Okay.
Yeah.
But I think that solution also have nuts and bolts, the one I'm talking about.
Anyway, it's not a black hole.
Okay.
Okay, so mine is more a curiosity. So people in the literature always impose that m plus and m minus are coprime.
Yeah.
But what prevents someone just to take n plus equal to n minus? Like,
Yeah.
is that where is the problem arising?
Yeah, you want.
Or did you actually get something that is actually in other space? I don't know. So why can't you get n prime equal to n minus, n plus equal to n minus?
Yes, we can do this formally, and there's a limit to obtain the spherical bolts in this case, or the two spheres from the spindle. But in general, if you have common factors between n plus and n minus, this means that you have an action of the space, and so there is a global quotient, which is the greatest common divisor of this space.
Okay.
So I have a backup slide on this, just to be clear, which is this one. This is for the branched length space, but the idea is the same. You have some identification, like this and this. But if there are some common factors, you are left with the identity action on one coordinate, but there is still some action on the other one.
I think the very short answer is that yes, you can take them.
Okay.
Okay. You can indeed, if you do that for this length space, you obtain exactly the branchless space, so you have singularities.
Function on the QFT side, there is no problem.
Yeah.
More questions? If not, let's thank our speaker.